so at this point we know what it means for a matrix to be diagonalizable. It's similar to a diagonal matrix. What we want is a way to figure out when a matrix is diagonalizable and how we can find that P matrix, that change of basis that makes it diagonal, and what will the diagonal matrix be, what will be the entries on the diagonals. All right, to get to that we need a tiny bit more vocabulary. But it will, of course, have to do with eigenvalues and eigenvectors. So let's take a square matrix. And I'm going to take lambda to be one of its eigenvalues. So lambda is a root of a polynomial. It might be a repeated root. X minus lambda might be there multiple times in the factorization. The number of times it appears, that's going to be the multiplicity, the algebraic multiplicity of lambda. Alright, so it's the number of times x minus lambda appears in the factorization of PA of x. Now there's going to be a second multiplicity, a geometric multiplicity. Now that one has to do with the eigenspace. It's going to be the dimension of the eigenspace. So how many elements are in the basis for the eigenspace corresponding to lambda. Alright, so let's try an example. Let me make sure I take the same examples you guys have. So 2, 4, 0, 2. Alright, and lambda equals 2. Let's find the algebraic multiplicity first, and then we'll find the geometric one. Alright, so to find the algebraic multiplicity, I must compute the characteristic polynomial, and I need to figure out how often it would be divisible by x minus 2 in this case. So PA of x is the determinant of a minus xi. So 2 minus x, 4, 0, 2 minus x, and I will get 2 minus x times 2 minus x. That's this one, and then minus 0, and so I get x minus 2 squared. Alright, so when I factor PA of x, which wasn't too hard here because it comes factored, I have x minus 2 there twice. That means this power here is going to be your algebraic multiplicity. So the algebraic lambda equals 2 is 2. Alright, so algebraic just means the number times x minus 2 was a factor. We have it twice. Now, to find the geometric multiplicity of lambda, I need to look at the eigenspace corresponding to 2 and to see how big it is. Alright, so to find the dimension of the eigenspace, I must find a basis for it. We've done it a few times. The eigenspace is the null space, so I need to reduce A minus 2I. That matrix, I'm just going to plug in 2 into that determinant here, will be 0, 0, 4, 0. That's reduced. So in my reduction, I have one free variable. The first column is all 0, so I have a free variable. That means my null space will be xy equals 0, 1 times s. Oh, sorry. Let me do it the wrong way since I've just messed up. Let's say this is x, this is y. We have x equals s. We have y equals 0. So xy is 1, 0 times s. And so my basis would be every vector that's multiplied by a parameter. So the basis for the eigenspace corresponding to 2 would just be 1, 0. And so its dimension, the dimension of that eigenspace, that would be 1, and that's the geometric multiplicity.